So it is my pleasure to introduce Professor Rafal Kulik. So he is professor from Department of Mathematics and Statistics in University of Ottawa. He is well known for his significant contribution in limit theorems for dependent random variables, long memory and heavy-tailed time series, extreme value theory, functional data analysis, etc. He has also co-authored a couple of books from Springer. So, I mean, they are heavy-tailed time series and long memory processes. So it is our pleasure that I mean we have Professor Rafal Kulik in this conference. So please, I request you to start your presentation.
Hi, good afternoon, good morning on my time zone. Can you hear me properly?
Yes.
And can you see the slides?
Yes.
Thank you. So first of all, I would like to thank the organizers for the invitation to give a talk at this conference. I just watched two other talks before, and it was pleasure to learn on topological data analysis. My talk will be on a little bit different topic, a little bit more classical, with much simpler formulation, but quite technical solutions from mathematical point of view. I will present this problem in the simplest possible version. There are extensions in higher dimension, there are extensions for functional data, but this will become much more and more complicated from technical point of view. So this is based on the joint work with my PhD student Klemenel Bilai and co-supervisor Gail Ivanov. Klemenel just defended his PhD thesis, which dealt with heavy-tailed time series and long memory. So very briefly, what I'm going to do in my talk, I will recall, for most of you, this is, I presume, quite known, what are the typical features of financial data. Then this will motivate me to introduce so-called long memory stochastic volatility model. And then I will talk about estimation of a value at risk, about some properties, some theory, very little, just to point out what is going on. And then there will be some mention of simulation studies. So again, this is something that I presume most of the people in the audience are familiar with. So let's look at so-called typical features of financial data. And again, I will do everything in one-dimensional setting. In multivariate setting, you have more and more features coming into the game. So we focus just on one dimension. So this is a typical picture of in this case, Dow Jones index between 2000 and 2010. But again, you take this type of data from stock exchange, and they will look very similar. So of course, this time series that you see here is not stationary; it has trends. So we have to kind of somehow do sort of stationary transformation. And this was presented already in the previous talk. What do you do? So we take the so-called log transformation, log return transformation. So you take the stock price today, divide by stock price yesterday, and take the log of it. This transformation should lead to stationarity, and this is on the top left side, we have the picture of this data. So you see that they oscillate around 0, and there are no significant trends, but you have some clustering of large values here, some clustering of large values here, and a couple of isolated large values. So when you do very simple statistical analysis, like QQ-plot, you will notice that the data are not normal. Okay? So this is what I think everyone working with financial data agrees with. But also, when you look at the correlations of the data or correlation of the squares of the data, you see two different things happening. So there is little correlation in the data itself, but the square data are highly correlated. Okay? So this is what I try to summarize here. We have uncorrelated log returns. We have a lot of correlation in the squares, and I say that we have long memory in squares, and then we notice non-normal behavior, and this induces possibility of so-called heavy tails. I will formalize this a little bit later. Now, I want to point out that, well, people doing financial time series, they mostly work with Garch models. These are the most popular models. There is a Nobel Prize in economics for introducing these models. However, so Garch models can capture heavy tails. They capture correlation, non-correlation in the data. They capture some correlation in squares, but Garch models cannot capture long memory. So the picture that you saw before on the right top bottom right panel, this is not really consistent with Garch model. Okay. So Garch models cannot capture long memory. So the question is what we can introduce. Okay. So this is the typical picture for financial data. Correlation in squares, no correlation in the original data, long memory in squares, and heavy tails. Now, in the title I mentioned that we want to estimate risk measures, and I will introduce these risk measures a little bit formally later. At this point, let me quote some sort of summary from a technical report by Wolfgang Herrler and his student on value at risk and expected shortfall when there is long range dependence. So this is the title of this paper, and so the statement is as follows. So I will just read it. Our results suggest that for proper risk evaluation, the degree of persistence, so the degree of long memory, should be investigated, and appropriate modeling that incorporate the evidence of long memory or persistence should be taken into account. So this is the summary of the paper, but if you look at this paper, has quite a lot of citations, and the papers that follow this technical report, they have even more citations. Some of the papers that deal with value at risk and expected shortfall under long memory, they have for about 200 citations. But the point is that there is no theoretical background, there is no theoretical evidence for this statement. All of the papers that I saw in this context, they deal with simulations, and they deal with some modeling and empirical modeling, but there is no formal theory to quantify what does it mean that long memory influences estimation of risk measures. And I will try to argue that this picture is not completely obvious. It is not obvious that long memory will influence estimation of risk measures. Okay? So the motivation stems from this paper and a lot of other papers that follow up this technical report. Okay, so I need to introduce some background. First, the model that captures the financial features of the data, and second, I need to introduce formal definition of the value at risk and the expected shortfall. So how do we model the features that we observe in this financial data? Well, I'm going to model it by so-called long memory stochastic volatility model. So there are two parts that come into the game. So first of all, we have the sequence yj, which has this linear representation. So this is nothing else but infinite order moving average, and this is a Gaussian process. Okay, so yj is a Gaussian process, Gaussian sequence, and the strength of the dependence is modeled by these coefficients ak. Okay, so the coefficients have to be summable to 1. I mean, they have to be summable at the first place so that the sequence is well defined. We assume that they are summable to 1, and they have particular form. So they decay to 0 at some relatively slow rate. So you can see here that ak is k to the power d minus 1, where d is between 0 and 1/2. The idea is that if d is close to 0, then there is relatively fast decay of the coefficients, and this gives fast decay of the covariances. When d is close to 1/2, then there is a slow decay of the coefficients, and this implies slow decay of the covariances. So the parameter d is, for those of you who are a little bit familiar with this or with long memory time series, the parameter d is called the fractional integration parameter, and it measures the strength of long memory. And again, d close to 0 means little memory, d close to 1/2 means a lot of memory. In particular, if you look at the variance of the partial sum, which in a classical case of independent data would be just n, in the long memory case, the growth rate of this variance is n to the power 2d plus 1. So because d is between 0 and 1/2, the growth rate of the variance is certainly faster than n. And again, n is the classical growth rate for independent or weakly dependent data. So to summarize, we are going to model long memory by introducing Gaussian sequence, which has slow decaying correlations. And the most important parameter there is this d, this fractional integration parameter, which is between 0 and 1/2. The second ingredient that is going to take care of the heavy tails is a sequence of independent, identically distributed random variables. For a moment, we don't assume anything about the marginal distribution. It will come in a moment. And then how we are going to define long memory stochastic volatility model. Well, we take a function phi, which is non-negative. It has to be non-negative because it is related to volatility, to squared volatility. And we define the sequence xj as the function phi of the long memory sequence multiplied by the noise. Okay. Now, in the classical formulation that dates back to the paper by Bright, Crato, and De Lima, the function is just the exponential function. But there is no really restriction on what you can choose here. And there are two situations that people consider. One situation is when there is no dependence between the long memory volatility part and the noise, and this is called LMSV model. And the second situation is so-called model with leverage. So the leverage is the specific financial feature of specific feature of financial data, and this can be also incorporated in this model by considering some dependence between y and epsilon. Remember that these variables eta, they define the sequence y. So the dependence between eta and epsilon implies the dependence between y and epsilon. So to simplify things as much as possible, I'm going to consider the model without leverage, but all of the results are in fact valid for models with leverage, but you have to be careful how you specify the dependence structure. So this is the classical formulation of the stochastic volatility time series, and because we have long memory present, we call it long memory stochastic volatility model. So is this model going to capture the properties that we noticed on the second slide of this talk? Well, if you look at the correlation of covariance, this is the formula for the covariance of this time series defined on the previous slide. You have to remember that typically in the modeling of these log returns, the expected value of the noise is 0. So if you look at this formula for the covariance is 0. Okay, so again, remember that typical feature of the financial data is that the log returns have very little covariance, very little correlation. So you can model it using long memory stochastic volatility model. But if you take the squares, then the covariance of the squares is a constant, which is non-zero, times the covariance of some function of the Gaussian long memory sequence. So the squares capture the covariance from the long memory sequence. So in other words, this model introduced on the previous slide can capture long memory in financial data. So long memory model consists of two parts. Long memory stochastic volatility model consists of two parts. Consists of function of the long memory sequence, and this part is responsible for long memory. And there is the noise that we are going to assume something about this noise in a moment, and this will capture the heavy tails. So what we are going to assume is that the tail distribution of the noise is like x to the power minus alpha. There is some slowly varying function. You can think about that this is a constant. This is not really important for in this talk. So again, the tail of the noise is roughly x to the power minus alpha, and this is the indication of heavy tails. This index alpha is a positive index, of course, and this is called the tail index. And the idea is that the smaller the tail index is, the heavier the tail is. The smaller the tail index is, we have more chance to get large values in our stochastic volatility sequence. Okay. And typical examples will be the Pareto distribution, or familiar to all of you, t-student distribution, and actually the number of degrees of freedom in the student distribution corresponds to the parameter alpha. Okay. Now, there is so-called Breimann lemma that links the tail of x with the tail with the noise. Because again, our model is for x. There is some assumption on epsilon, which is the part of the model, but we want to, at the end of the day, we want to have the heavy tails for random variable x. And there is the so-called Breimann lemma, which tells you that the tail of x is comparable to the tail of epsilon. Okay? So in other words, such constructed long memory stochastic volatility model captures not only the long memory in the data, but also captures the tails of the financial data. Okay? And this model was, again, it was originally in the short memory case, it was introduced by Bright, Kratel, de Lima about 20 years ago. But then we extended this to long memory to capture what you really see in financial data. And you can make this model more and more complicated. You can do a multivariate version. We're also working on some functional version. You can mix the features. You can also put heavy tails in the volatility part. So you can make this more and more complicated. But again, for the purpose of this talk, I try to keep this as simple as possible. Okay, so we have a model that we are going to work with. And now let me recall the definition of a value at risk and expected shortfall. Again, most of you working in financial risk management are familiar with these risk measures. So value at risk this is nothing else but a quantile, so the inverse of the distribution function. And so the value at risk at level P, this is the quantile at 1 minus P, and I denote this as Q sub X at 1 over P. The idea for this notation here is that what we are really interested in risk management is what happens when P is small. So typically you hear about value at risk at level 99% or 95%. This corresponds to P equal to 0.01 or 0.05. Okay, so we are interested in P small, and then this value 1 over P becomes big. So we are looking at quantiles at the tails. Okay, so we are looking at large quantiles. So this is the definition of a value at risk. Simply speaking, this is the quantile at the boundaries. And the second part is the expected shortfall. This is the conditional expectation of X given that X is bigger than value at risk. There is a lot of discussion what should be used. The issue with value at risk is okay, value at risk is very simple. The formulation is simple. The estimation process is relatively simple, and also backtesting is relatively simple. However, this is not a coherent risk measure. In case of expected shortfall, this is a coherent risk measure, but it is, for example, the backtesting is not obvious how to do this. So I'm going to focus just on the value at risk in this talk because of the time constraints, but a lot of results can be repeated for the expected shortfall. So to summarize, I have a model for financial data, so-called long memory stochastic volatility model. And my goal is to use this model to estimate value at risk and to see if long memory plays some role in estimation. So this is what I'm trying to write here. So again, we have a stationary data, so long memory data, and we want to estimate value at risk. If we know what the distribution of X is, then we have a bunch of parametric methods. Because again, value at risk, this is a quantile, and if we have a parametric model for the distribution of X, we also have a parametric model for the quantile. However, in stochastic volatility models, the analytical formulas for the tail distribution are rather not available. We have the asymptotic behavior, but not the analytical formula for the tail distribution. So the parametric approach is rather not possible. So we are going to use the model assumption that I made in equations 2 and 3. So the model assumption of the tail behavior. And these model assumptions are referred as the regular variation. Okay, so I'm going to assume that the tail is roughly x to the power minus alpha, and I'm going to use this information to construct semi-parametric estimate. So what would be one approach? to estimate the value at risk. Recall again that the value at risk is nothing else but the quantile at high level, which corresponds to small p. So the most natural approach would be, okay, let's order the data in the increasing order. So we consider order statistics, and the estimate could be just this order statistic. So I calculate n times p, and I evaluate this order statistic. The issue, so this is fully non-parametric approach, which doesn't really use anything about your model. So you take the data, order them, and take the appropriate order statistic. The issue with this is that this is rather useless when p is small. And again, we are interested in small values of p when we estimate value at risk in the context of risk management. The issue with this approach is that when p is small, n times p is also small. Often this is smaller than 1. So no matter what p, so as long as p is small, no matter what it is, you will always estimate value at risk using the largest observation. Okay, but also what can happen is that the theoretical formulas for the value at risk are different, significantly different, but you will always estimate them by the largest observation. Okay, so this is the big limitation of this, I would say, standard approach to estimation of a value of a quantile. So we are going to use regular variation and do something more clever. So the idea is as follows: the level p will depend on n and will go to 0, and k will be a sequence that goes to infinity but slower than n. And then we can have this approximation. So the value at risk at one level, at the very high level, can be compared to value at risk at so-called intermediate level by this scaling formula. So again, this is very intuitive what we are doing here. At high levels, so if you want to model very extreme observations, if you want to model the quantile at the very tails, you don't have observations there, so you kind of use the shape of the quantile function to go to the intermediate order statistics. And this is actually expressed here in this approximation. So this approximation suggests the following estimator of the value at risk. Well, you take the intermediate order statistic and you scale it appropriately. So you scale it and you have to put 1 over alpha here. Again, alpha is the tail index. We don't know it, so we need to estimate it. So this is the classical semi-parametric estimator in the context of regular variation, in the context of heavy tails and value at risk estimation. So in order to study this, in order to say something about the behavior of this estimator, we need the asymptotic theory for sample quantiles, because they are here. We need the asymptotic theory for the tail index estimation. So we need 2 ingredients, and this is relatively well studied in the IID case and in case of weakly dependent data. The limit theorems are known, and we know what is the limiting variance, so we know what is the influence of weak dependence. Now, what do we have in long memory? So we need to introduce a technical tool to deal with intermediate quantiles. This is not exactly the same theory as standard empirical processes or standard quantile processes. vis-a-vis so-called intermediate quantiles. So we look at the extremal behavior. So what we are doing here, because we look at extremal behavior, we are going to take the sequence, the threshold sequence going to infinity in such a way that n times the tail also goes to infinity. So un has to go to infinity, but not too fast. And when I consider this object, t and tilde, it looks like the empirical distribution, but this is called tail empirical distribution. Why tail empirical distribution? Well, you look at the tails, okay? And note that the scaling is different than in the classical empirical distribution function. But in any case, this is very similar to the classical empirical distribution. Again, instead of the distribution, we look at the tail and we look at extremal behavior. Now, so if you take the expected value of this object and you let n to infinity, you recover the tail behavior. Okay, so this empirical tail distribution function in the limit captures the tail behavior. So this definition makes some sense. Okay. And now let me quote. As I mentioned, we need behavior of quantiles. We need the tail index, and everything is related to the so-called tail empirical process. So what do we do here? I state the result for weak dependent case, for example IAD case, to just tell you what the typical limit is. So you have the scaling, which is not square root of n as in the classical theory. You have a little bit smaller scaling, and you take the tail empirical distribution, you center it properly, and in the limit you get the time changed Brownian motion. Okay, so in the classical empirical processes, you get a Brownian bridge. Here you get time changed Brownian motion. Okay, so this is the classical result under IAD situation, and so this is nothing really new in the talk. But I put this result to have this as a benchmark for another result. Okay, so there are some technicalities related to long memory, and I will try to kind of go a little bit faster through this. So what is important in the long memory situation is so-called Hermite rank. And this, so you look at the behavior of the expected value of the function applied to a normal random variable multiplied by so-called Hermite polynomial. And again, because of time constraint, I cannot really go into the details. What is important, just let me give some examples. If I take the linear function of the exponential function, the Hermite rank is 1. But if I take the quadratic function, the Hermite rank is 2. Why do we bother about this Hermite rank? Well, this plays a crucial role in asymptotic theory. So we will see this in a second. So the type of the function that you use to model volatility will play a role. And how does it enter the asymptotic theory? Well, I introduce the sequence A and tau, and you see this kind of strange power here. This, in the classical situation of weakly dependent data, it will be n to the power 1/2. And here you can see, if you look closer, if D is bigger and bigger, then this has influence on the sequence. And also the Hermite rank has influence on the sequence. So this is quite a complicated function of D and tau. And another ingredient that we need is this complicated so-called Hermite-Rosenblatt process. This is a multiple integral of a Brownian motion. Okay? And as I said, this is called Hermite-Rosenblatt process. Now, there is kind of long, old result that tells you what happens in non-memory, how non-classical the limit theorems become. come. So if you take just the partial sum applied to long memory sequence, in the classical situation, the scaling will be square root of n. So we have different scaling here, and we have the limit, which is very, very complicated. Okay? So not going into the details here, the long memory, so the strength of length long memory, which is parameter d, and other parts of the definition of long memory, like Hermite index, influence the limit. And the limit can be very complicated. It may not be normal at all. So as I said, this doesn't look like standard central limit theorem. So this makes long memory quite complicated to work with, because often in the limiting behavior, you get something which you cannot really estimate. This is very complicated object. Bootstrap doesn't work, so there are no classical tools to work with. Okay, so let me state what happens with the tail empirical process under long memory. We have two, so the resulting theorem 2 is kind of a little bit disturbing, because the long memory influences the behavior of a tail empirical process, which is not very good, because again, this object here is extremely hard to estimate. You cannot get the quantiles, you cannot do bootstrap, most of the things do not work. So there are two parts of this theorem. We have one condition on the rates of so this is the balance between memory and tails. This condition here tells you that the tails dominate. Okay? In this case, the limiting result is the same as for the independent case, so there is no influence on long memory. In the second scenario, this assumption means that the memory dominates, long memory dominates here. In this case, the tails do not matter, there is a different scaling, and in the limit, we have kind of complicated random variable. But again, it is you cannot calculate the quantiles, you cannot bootstrap. So for the tail empirical process, which is the standard tool that we will need in a moment, the long memory enters into the game, which is not very desirable. However, and this is kind of very nice thing that we were able to find out. Well, the tail empirical process, this is not precisely what you want to look at. You want to look at so-called tail empirical process with random levels. What's the point? The point is that in the formulation before, we have this scaling sequence. And well, we don't know what it is, because this is, you need to know what is the tail distribution, and you don't really know what it is. So the typical trick is that you define so-called tail empirical distribution with random levels. So you fix k, which is the number of order statistics that you are going to consider, and you take the kth largest order statistic, and you look at the observations that exceed this random threshold. So basically speaking, what we are doing here, we restrict the number of observations. We drop the small observations from our data. Because again, in the value at risk estimation, when p is small, we are interested in high values, so we drop the small values. So what happens in the next theorem is extremely interesting, because it tells you that, okay, there is some technical condition that this is related to the bias. It has nothing to do with long memory. It tells you that when you consider the random levels, the tail empirical process with random levels, then the limit is a time-changed Brownian bridge, and the limit is the same as in IID case. So the long memory is gone. The long memory in the tail empirical process with random levels vanishes. There is no influence of long memory here. And again, this is very nice feature because long memory is extremely hard to estimate. Even if you want to estimate the fractional parameter d, the estimation is often very imprecise. So it is nice to have results that tell you that long memory do not matter. Okay. So how do we are going to use this technical mega theorem? Well, recall that the estimation of the value at risk consists of two parts: the quantiles and the tail index. The tail index can be estimated using so-called Hill estimator. The reason for this is that the limiting function in the centering is integrates to alpha minus 1. So the estimator can be constructed by integrating the empirical version. So this is the famous classical formulation of the Hill estimator. You see this is the function of order statistics. But what is more important is that this is the function of the tail empirical process with random levels. And remember that there is no long memory here anymore. So this is not a surprise. The limit that we get, the central limit theorem for the estimation of the tail index, is free of long memory. The limit theorem that is presented here is the same as in IID case. So we have nice limiting distribution that depends on the unknown parameter. This is another issue, but we completely get rid of long memory. So in other words, the tail index can be estimated, and we don't need to worry about the long memory. And this is extended to other features, other external features, other estimators of the tail index, estimation of the multivariate tail dependence. So this is very, very nice feature that in estimation of of the external parameters, the long memory do not play, so long memory does not play a role. And again, this is, I think practically this is very, very, very important. So the tail index, the first ingredient of this of the value at risk estimation of estimator. So the tail index can be estimated using the Hill estimator or other estimators, and long memory do not matter. However, we have also a second ingredient, which is the quantile, which is the order statistic. And unfortunately, the limiting distribution of this order statistic, sorry, there's kind of notation that is, so this is the order statistic here. Unfortunately, the limiting distribution of the order statistic is influenced by long memory. Okay, so the tail index is not influenced by long memory. The quantiles are influenced by long memory. So how this influence can be quantified? Well, let me show three theorems. And the theorems look a little bit ugly. This is what it is. But I will try to give you some idea what is going on. So I'm going to consider the long memory stochastic volatility model. I have normal random variable and have a parameter mu, which is between 0 and infinity. And there are different limiting scenarios. So the first scenario is that the number of order statistics is comparable to n times p. And this parameter mu is between 0 and infinity. This is not the classical setup in the extreme value theory, because you will see in a moment that what we want is a little bit different condition, but this is kind of important for simulation, because in the simulation studies, we have fixed number of k. Even though k has to go to infinity, the number of order statistics that you take will go to infinity, but still in the finite sample, k is fixed. Yep. So now this condition means that we have a weak long memory. Okay? So if we have, so these two conditions together mean that we have weak long memory. In this situation, the value at risk can be estimated in the very same way as in IID case. So again, long memory, weak long memory. So this is the situation when the tails dominate. The value at risk can be estimated, and we don't in the very same way as in IID case, and you don't need to worry about long memory. However, if the long memory dominates, then, well, there's a different scaling factor, and in the limit theorem for the value at risk estimator, the limiting distribution is this complicated object that I introduced before. Again, this object, you cannot really do anything about this. So this is extremely hard to work with this object. So again, if in this situation that the number of order statistics is comparable to n times p, n is the sample size, p is the level in the value at risk, and if the tails win, there is no influence of long memory. If the long memory wins, this is expressed in the limit. So let's go to another situation. So this is the classical setup of extreme value theory. K goes to infinity fast enough. The number of order statistics goes to infinity faster than n times p. And again, if the tails win, so the long memory doesn't matter, and this is the limiting theory, the limiting result. You see there's a little bit different scaling here. There is this additional log factor. But again, the limit is the same as in IID case. If the memory wins, well, this would be the classical scaling, but you don't really get anything in the limit. Okay? So the limit becomes degenerate. So what happens? So let's go look a little bit closer in the situation when the long memory wins. Well, you have to be a little bit careful to what you assume on the rate of the long memory, and then you can recover with a different scaling. You can recover again the complicated random variable. So we have three theorems which are very technical, and the proofs are very technical. But so let me try to summarize what we see here. So long memory. So this is the bad message. The long memory influences estimation of the value at risk in a very complex way. So you really need to be careful what is the relationship between the tails and the long memory. So there are a couple of scenarios. In one scenario, both order statistics and the limiting result comes from the order statistics and the tail index. In one scenario, the limiting behavior comes only from the order statistics. In another scenario, the limiting behavior comes only from the tail. Okay. Now, again, this is a kind of bad message. However, if we go back again to the formulation, we still have some scenario when the long memory is killed by the tails, and we have still some room to maneuver to get the limits that do not fill long memory. So if The message here is that if the long memory is not very strong and the tails are quite heavy, you don't need to worry about long memory in the estimation process. If the long memory is quite strong, you need to worry. But the question is, if long memory is extremely strong, is this a real long memory, or this is related to trends? I would, let's say, if I get the estimator of D close to 1/2, I would probably not use it in my estimation process, because probably there are some trends in our time series. Okay, okay, so I will finish in 2 minutes. So again, long memory comes into the game in a complex way, which is a bad message. But the good part of it is that if long memory is not extremely strong, you still don't need to worry about it. So let me show you some simulation study to illustrate the point. I consider this stochastic volatility model. I play with different noise, with Pareto or student noise, different correlation. So I consider different parameter D close to 0 weak memory, D close to 1/2 strong memory. If you do simulations for tail index, you will not see long memory at all. So let's see what we can see for value at risk. So I just, instead of having tables and numbers, I just present the box plot. On the left panel, you have weak long memory. On the right panel, we have strong long memory, and going from the top to the bottom, we have more and more order statistics. So the message, what is the most important thing here? The variability on the right-hand side is bigger than on the left-hand side. So the long memory introduces more variability, but you really need to have a strong memory like D equal to 0.4. So this is the confirmation of what we have in the theory. This is the simulation for value at risk. I didn't present any results for expected shortfall because of time constraints, but quantitatively, the results are very similar, and this is again expressed here. On the right panel, which corresponds to strong memory, the variability is bigger than on the left panel, which corresponds to weak long memory. So in summary, long memory enters we can quantify how long memory enters the estimation of the value at risk of the expected shortfall. So the influence is very complex. This is the bad message, bad news. The good news is that if long memory is weak, you don't need to worry about it. So which is practically, I think, quite important. So that's all what I had to say. Thank you very much for your attention.